And welcome back again. Today we're on this video, I'm going to try to wrap up the conversation about the cosmic microwave background. The CMB is an incredibly rich subfield or topic within cosmology, and I'm not exactly doing it justice, but hopefully you'll have gotten a good overview of what it's all about. So to wrap things up, I'm kind of going to take us through the end of Chapter 8 in Barbara Ryden's book and give a qualitative answer to some questions that you might have. And just to give a sense of scale, this is a table that came out of Ryden's first edition of the book, and these numbers have shifted slightly in the second edition of the book because new and presumably better data has become available, but the numbers have not shifted by much. I just want us to focus on kind of these more or less three distinct times within the evolution of the universe that is relevant for the cosmic microwave background. One is in the early universe, radiation, the energy density in radiation dominated over all other forms, but because it scales like a to the minus 4 and matter scales like a to the minus 3, at some point the matter energy density and radiation energy density were equal to each other, and then at all times later matter dominated. And anyway, the time at which that happened, or specifically the redshift at which that happened, apparently was around 35 or 3600, Z of 35 or 3600, which was at a temperature of about 10 to the 4 Kelvin. And that occurred at a time that was like 50,000 years after the Big Bang, or about 0.05 mega years after the Big Bang. Okay, so it is after that point that the cosmic microwave background occurs. In other words, when last scattering occurred. So after matter radiation equality happened, there was this time that we'll define as recombination, when approximately half of the baryons were ionized and half were in neutral form. That's not precisely when last scattering occurred, but it was around that time. It sort of sets a closer sense of scale. It's like 13 or 1400 redshift. But precisely when photons decouple, that's when the interaction rate of photons with the plasma dropped below the Hubble rate, and that's more or less when the last photon scattered off of the CMB. Really, that wasn't a particular instant in time, but it actually happened over a finite range, and that's why the surface of last scattering is actually it actually has some thickness, and that can be quantified with something called the optical depth. But anyway, the thing to really get away from this, or take away from this, is that the cosmic microwave background was formed at a redshift of about 1100, and the temperature was about 3000 Kelvin, which is quite high compared to our day-to-day, average room temperature, right? That's about 10 times hotter than room temperature is, but it's going to turn out to be much lower than the temperatures at which Big Bang nucleosynthesis occurred. Okay, let's go forward then. So one question that you might have is, what do the angular sizes on the cosmic microwave background temperature maps, like the things I'm showing you now, how does that correspond to real physical lengths? So we have this kind of picture. So let's analyze that. So remember that we have this kind of picture in mind. If this is you, and you're looking a little bit orange, that's okay, and you're looking out at something that's at some distance away, we have this kind of picture, right? An object that subtends a particular angle on the sky, we'll call that delta theta, might have a real physical size that we'll call L, and we can define something called the angular diameter distance, which it's defined in the same way that it's defined in flat space, but this definition is a general thing that it can be defined for any kind of space-time, but the angular diameter distance is defined as the let me get this right. I guess, well, the definition of the angle is the physical size over dA, or you can write dA as that physical length divided by that angle. Okay. That being said, we also had a relationship between the angular diameter distance and the proper distance. If you recall, that was something we did back in Chapter 6, I believe. This involved the proper distance, whatever that is today, divided by 1 plus z. Again, z, the redshift, that corresponds to the redshift of a photon that was emitted then, whenever it was emitted to now. Okay, so here we go though. If we're interested in physical sizes on the cosmic microwave background, that means that we are interested in things that with a redshift of about 1100, in fact, we'll use 1090, which is closer to the more precise number. If you recall, in the most recent homework set that was based on Chapter 8, we saw that the distance, the proper distance to the cosmic microwave background, is actually damn close to the horizon distance today. That is to say that this is approximately d horizon. What we saw was that actually, there is a correction term here, but it's relatively small. Correction term that involves the distance that light would have traveled from the Big Bang to the time when the cosmic microwave background was formed. Well, it was formed at something like 300,000 or 400,000 years. That sounds like a lot, but it's actually quite a short time compared to the age of the universe, which is like 14 billion years. So this is a pretty decent approximation. So the proper distance to the CMB is about the horizon distance, which is approximately 3.2 c times h naught inverse. This is something that comes from the benchmark model that Ryden talks about. And there we go. I guess we're almost ready to put all these things together. That means that dA is approximately equal to, 3.2 times h naught inverse divided by, I'll write this as 1091. It's not that much different from 1090. Another way to say that is what's in the bottom. You could approximate that as z if you wanted for large z. But anyway, we might as well stick that number in. This works out to be approximately 12.8 megaparsecs. That's a good number for you to compare. All right, so this angular diameter distance is that number. That's that kind of distance. That's not the distance the cosmic microwave background is away from us. That number is something more like the proper distance. This is the so-called angular diameter distance. Which is not the same, right? The difference here has to do with the fact that we have a curved space-time and expanding space-time. What we're interested in doing, though, is using that value and putting it into this equation to see if we can understand how do the physical length scales correspond to the angles that they subtend. So let's indicate that here. So apparently L must be equal to, right, this is the angular diameter distance times the particular angular size of something on the cosmic microwave background. That must be this 12.8 megaparsecs times the angle, and that angle is measured in radians. And so the way that I want to do this is just indicate that's what I'll do is divide this by radians so that we know that's the unit we'd be using. And let's turn this into degrees because that's the resolution that we're told that the Planck satellite had when it was looking at the cosmic microwave background, had a resolution in degrees. So at least we can figure out what the resolution of the experiment, how that corresponded to a physical size. So let's just multiply this by units to convert this, to get the angles written in terms of arc minutes. So pi radians per 180 degrees, and remember 1 degree is equal to 60 so-called arc minutes. What that means is we can put this together, and this is 3.7 or so kiloparsecs, delta theta in units of arc minutes. And it turns out that the Planck satellite was able to, right, it's angular, it didn't have infinite precision, but it could measure the difference in temperature from one spot in the sky to the other at a scale of about 5 arc minutes. So I'll just write that down. Planck resolution. Again, this is the Planck experiment, the Planck satellite. Experimental resolution. Delta theta was approximately 5 arc minutes. And so that tells us what kind of length scales it was able to get. And in other words, the smallest length scale that the Planck satellite was able to measure was approximately 19 kiloparsecs. So let's think about what that means. This experiment, looking today at the cosmic microwave background formed back then, was able to see things that are as small as 5 arc minutes. That corresponded to physical sizes that were separated by 19 kiloparsecs back then, at the time when the cosmic microwave background was formed. So that's back then. So that means that would correspond to a physical size today, L times the scale factor today compared to the scale factor at the time of last scattering. That's the size today. That would be, by the way, L times the 1 plus Z at last scattering. In other words, L, that 19 kiloparsecs, times about 1090 or 1091. You could stick in those numbers and convince yourself that this is about 20 megaparsec. So those, right, that's quite large. That's sort of the scale of big galaxy clusters. Or I'll just write galaxy clusters, right? So galaxy clusters. Remember that the sort of the scale of length between us and the nearest galaxy, the Andromeda galaxy, is like 3/4 of a megaparsec, but the size of, you know, a large cluster of galaxies might be tens of megaparsecs large. All right, let's go back to the next, back to the slide, whatever the hell this is, and ask what the next question is. So another question that someone might ask, and this is not going to seem like an obvious question, but once we talk about it, you'll see that this is kind of odd. How much of the cosmic microwave background was in causal contact with itself? What I mean by that is, well, let's calculate this, and then we'll give some interpretation. So the reason why this is interesting, though, is that the cosmic microwave background is more or less uniform in temperature to about 1 part in 100,000. The little speckles that you're seeing on the screen right now show the anisotropies. Those are the deviations from this mean temperature of 2.7255 or whatever the number is Kelvin. But it's quite uniform all over the sky, and that would be totally something you'd expect, for example, if you had a swimming pool or this, you know, a gas in a room like the one I'm in right now, and you could say, well, it's all at the same temperature. And that's not surprising at all, because there's been plenty of time for the material, the gas in this room, for example, to come into thermal equilibrium with itself if it wasn't already. And lots of time for interactions here to affect interactions over here, interactions over here. But the Big Bang happened at a finite time ago, and so, well, given the fastest thing that can move is light, how far could light have gotten from the Big Bang to some, well, how far could it have traveled over the course of time between the Big Bang and when this last scattering surface was created? So let's go ahead and talk about that quickly. So the scale of causality. So what you might be interested in something which is what is the horizon distance at the time when the cosmic microwave background was formed? In other words, at the time of last scattering. Okay, that should tell you how far light has traveled since the Big Bang. Well, that should be given by, we've done this a bunch of times, this integral of c dt divided by the scale factor. And you integrate from the emission time, that's the horizon is given by, you know, light being emitted as early as it could possibly be, and observed when, well, it would be, you know, observed, or it would have gone as far as it could in the time to the last scattering surface. Lastly, this quantity alone is just a co-moving distance, and to make sure it's a physical distance, that does have to be multiplied by the scale factor at the time when you're interested. In other words, the scale factor at the time of last scattering. Okay. Now, what you may want to do, and I encourage you to do this, is you can verify this by verify with Ryden equation 5.109. This is, you may want to do this for fun. I think it's a good idea. That equation will tell you how the scale factor evolves in time in a universe which only has radiation or matter, some combination. That's what you really need, because at early times you've got radiation domination, and then you transition through the matter into the matter-dominated phase. In any case, when you plug everything in, you can verify that this is approximately 2.24, says Ryden, times the speed of light times the time at which the last scattering surface was formed. When you stick in the fact that the last scattering surface was formed at about, well, 370,000 years or so, then what you'll find is that the horizon distance is approximately 0.25 or so, I'll put a 1 in there, megaparsecs. So from the time the Big Bang occurred to when the last scattering surface was created, light could have traveled 0.251 megaparsecs, which, by the way, should tell you that's the farthest that any signal should have been able to get, right? If I'm a place over here I'm at 3.8 Kelvin, or I'm at, I don't know, 3 million Kelvin, and a place over here says, well, I'm at 4 million Kelvin. You know, eventually, given enough time, these things will come into thermal equilibrium, but you know that can't happen any quicker than the time it takes for a signal to get from here to there. So let's take this a bit further. The horizon at the time of last scattering, 0.251 megaparsecs. Well, okay, what kind of angular scale does that correspond to. Recall that what we can do is relate the angular diameter distance to a physical scale. In this case, that's the horizon distance at the time of last scattering. And that should be divided by the angular extent that would take up on the sky. Let's flip that around, though, to solve, whoopsies, for the angular size that of the, if you like, the angular size of causality that we might be able to see on the sky. So that should be the horizon distance divided by the angular diameter distance. Well, now we have both of those numbers, 0.251 megaparsecs divided by that number 12.8 megaparsecs. Well, you know, that's about 0.02 radians. Okay, if you convert that to degrees, that's about 1 degree. So that's odd. It's incredibly odd. It's incredibly odd that although we see these speckles here, again, you've got this whole sky which has a uniform temperature, uniform to 1 part in 100,000. And as you're seeing here, this particular projection of, if you like, this sphere now made into this oval shape. I forget the name of this. But what we're supposed to believe, apparently, is that the cosmic microwave background could only have been in causal contact with itself over a patch of about 1 degree. Can I annotate this, I wonder? I don't know how. Okay, I'm going to draw another picture. It's incredibly odd because you've got this cosmic microwave background, and 1 degree takes up a patch of about this. So you might expect, it's potentially reasonable that you'd have uniform temperature within a 1 degree patch. But another 1 degree patch, which is, let's say, over here, or maybe all the way on the other side of the sky, 180 degrees separated from it. Somehow, these things have the same temperature, at least they are equal to each other with deviations only at the level of about 1 part in 100,000. So apparently, this patch and this patch, or any other 1 degree patch very far apart, or not that far apart, are causally disconnected. Again, because light would not have had the time to get any signal from here to get to there. It just could not have happened. And yet their temperatures are incredibly uniform. This is called, by the way, it's called the horizon problem. You know why it has the word horizon in it. And, well, it's a problem because it seems odd that the temperature would be that incredibly uniform. This is one of the major motivators for something called inflation, which we won't really get into in this course. There are some better motivations for inflation and some that aren't so good. But the fact that the whole universe, at least all the observable universe, appeared to be at nearly the same temperature, yet there's no causal mechanism to explain it, is quite odd. Okay, let's see. There's perhaps one last question to address. Oh, here it is. So we have this temperature map. You imagine you've measured temperatures at different parts in the sky. What do these different temperature fluctuations correspond to? So, okay, you have variations in temperature. What is their physical significance? We've talked about this horizon distance, and things were not in causal contact on scales larger than that. But certainly on scales smaller than that, there was plenty of time for example, matter, at least over-densities in the matter, to start to try to collapse, right? That's what, if you like, you got matter distributed, gravity wants to make things pull in towards itself. But at the time, there was this plasma, very hot, lots of pressure. And so as over-densities tried to collapse, they had their collapse halted and, well, repelled the other way by pressure. And this is something we briefly touched on. In equilibrium, that would be called hydrostatic pressure, but the dynamic version is that you got gravity pulling things in and pressure pushing things out, making oscillations. In fact, they're called acoustic oscillations. It's pressure waves that were created in the early universe as the result of gravity and pressure fighting against each other. There's a nice little picture that you could draw. It sort of has, the gravitating things, which is all the matter and radiation, and the dark matter trying to pull things in, and then the photon pressure pushing things out. And so what you end up with is regions with overdensities. Those you might call potential well, where things are trying to push in, pull out, and potential hills those would be the places where they're slightly underdense. But in any case, you're going to end up with pressure waves, and we'll get into that a bit more in chapter 11 and 12. But at least what I can say, I'll draw a quick picture, is that the time it takes for, some region of overdensity. So I'm just going to give you a cartoon picture, overdense cartoon. So, you've got some background stuff going on, but then in some region, there's some excess matter. And you know that gravity's going to try to pull all that stuff in. That's purple. Everyone knows that gravity is purple. And what's resisting this is pressure. And they're fighting each other. And the time scale over which it takes for it, to go through half an oscillation or a full oscillation, that depends on the physical size of the overdensity. So I guess the sort of rough thing I could say is that larger overdensities, in other words, physically larger their sizes, larger overdensities, take longer to collapse or take longer to oscillate. Than smaller overdensities. Again, these are overdensities with smaller physical size. So that being said, imagine you pick some amount of time that has elapsed after the Big Bang occurred. So really large overdensities might have only had time to, just get to collapse at that time. But much smaller things might have been able to collapse and bounce out and collapse and bounce out. And as you ask yourself, what do the different overdensities look like at the snapshot when the last scattering surface was created? The last scattering surface is kind of like taking a picture of what the overdensities looked like at that moment in time, about 400,000 years after the Big Bang. It's going to be a snapshot of some large overdensities having just reached their compression, some medium overdensities which are somewhere in between, some smaller overdensities which have gone through a few. And so that's actually what you're seeing when you look at the so-called power spectrum of the cosmic microwave background. Really, this is, if you like, the Fourier transform squared sort of this temperature map that you've been looking at this whole time. These speckles represent those different acoustic oscillations which occurred, and they're all occurring at different scales. The biggest ones seem to have occurred at a scale of about 1 degree, which is, comparable to the horizon scale at the time, but that actual size is governed by the speed of the acoustic waves in that plasma. But you'll see that there are other wiggles that appear at higher multipole moments which correspond to smaller angular scales. Again, those are corresponding to, at those higher peaks and higher troughs, actually the higher peaks correspond to those smaller overdensities which underwent a lot of oscillations, and then at the time that the last scattering surface was created, they had gone through, let's say, their second oscillation or their third oscillation. That's what the first, second, third peak corresponds to. So anyway, when these oscillations are going on, you're getting oscillations in density. Those oscillations in density correspond to oscillations in the gravitational potential, right? Where the density is higher, you expect the gravitational potential to be lower, deeper, if you like. And the regions where the gravitational potential is lower, the photons that came from there had to climb out of a higher potential well, and so they lost energy on their way out to get to us. So the logic goes something like this. The overdense regions made for lower gravitational potential, more negative if you like, and those correspond to actually colder photons that lost more energy on their way out of those potential well. I'll put colder photons. So what that means is when you were looking at the cosmic microwave background, and again, these images are always given with the average temperature subtracted, so the dark blue spots are cold and the ones that are yellow and red are hot. The cold spots correspond to regions that were overdense at the time, and the hot spots correspond to regions that were underdense at the time. Right. So that's what these wiggles correspond to, and we'll get into more of that when we talk about gravitational instability. The last thing I just want to mention, I think I had advertised this a long time ago in the class, is that as it turns out also the location of those peaks, in particular the first peak, tell us something about the overall geometry of the universe. So this lower middle picture gives you a sense of what the cosmic microwave background would look like if we lived in a spatially flat universe. On the left, you see what it would look like in a positively curved universe, and on the right, a negatively curved universe. I'm not sure if you can tell, but on that lower left picture, what happens is that a particular scale of a pattern on the cosmic microwave background today would look like it subtended a larger angle, and that is a result of having a positive curvature spacetime. And on the other hand, in a negatively curved universe, those scales would look like they took a smaller angle. Here's a probably better picture that might help to explain it. You imagine you had some kind of standard ruler, some object that would take up 1 degree of arc in, let's say, flat space. That's what that red line corresponds to, like that's what the sort of Planck satellite would be looking at. But for example, in an open universe or a universe with negative curvature, you would instead, the photons would travel more like along that gray line. And so what you would see would be something that would subtend a smaller angle. And that would take the corresponding power spectrum of the cosmic microwave background there in red. And it would not only, well, it would increase the amplitude, but it would shift things over to smaller angular scales. So the place where that first peak occurs in our cosmic microwave background really gives us a handle on the geometry of the universe. And so here is one particular plot of omega dark matter or omega lambda versus omega matter, and you'll find a similar figure in Ryden. But what it tells you is that using the WMAP satellite in combination also with the South Pole telescope, although there is some consistency you can get with a positive or negatively curved universe, it's hard to make it too positive or too negative without severely changing the parameters of the abundance of matter and cosmological constant. You put this in combination with the data that comes from supernovae and other things like baryon acoustic oscillations, and we really do seem to live in a universe that is is consistent with being flat and also consistent with having about 30% matter and like 70% cosmological constant, at least as for the simplest explanation for the universe that we live in.